how powerful is this DFA model? Can I compute anything with a DFA? Or are there some restrictions? What are the limitations of DFA, if there are any? So let me draw a picture for this. So we have the set of all languages. And in mathematical notation, the set of all languages, we can denote it by the power set of sigma star, right? Because a language, by definition, is a subset of sigma star. Therefore, the set of all languages is the set of all subsets of sigma star, and that's the power set of sigma star. Now, we know that some of these languages are regular languages. We've seen a few examples in this lecture. And the question is there anything outside here or not? So the question is, are all languages regular? Now, what is your intuition for this? You know, DFAs are a restricted model of computation. It seems like there should be some problems that a DFA cannot solve, right? And I completely agree with that. But now then the question is, how do we prove that, right? So this is now going to be our task, okay? We want to come up with a language that is not regular, and we want to prove that it is not regular. So I'm seeing already like prime checking. Very good. So now let's think about the task at hand, right? We want to come up with a language such that no matter what DFA you come up with, your DFA cannot solve this language. Seems like a very hard task, right? Like, how do we rule out any possible DFA? Like DFAs can have many states, millions of states, perhaps weird transitions. How can we reason? How can we argue against all possible DFAs? It seems hard, but we will be able to do it. And that's actually pretty cool that we can do it. Now, as you're approaching this, one first question, I guess, that comes up is, how do you choose your candidate non-regular language, right? So you want to identify some language and say, like, this cannot be solved by a DFA. Some of you already have given me, like, you know, let's say, primality testing. Now, there are a couple of strategies you can employ here. One strategy would be to actually pick a complicated language and say, like, you know, this is a complicated language, has a complicated structure, complicated definition. So therefore, a simpleton like a DFA cannot handle this language. Okay, but that wouldn't be a good strategy in my opinion, because if you pick a complicated language, your probably argument is going to be complicated, and maybe it's going to obscure the essence of what's going on. Right? So it's actually better to pick the simplest language that you can think of that really targets the weakness of the DFA, okay? So which means that you probably want to think about what are the key limitations of a DFA, and then with my choice of the language, can I target in the most simple way I can, target that limitation or limitations? Well, what are the limitations? I mean, I kind of told you at the beginning of the lecture. So one thing that we said is, you know, you scan the input once from left to right and you have to make a decision. But that wouldn't be a problem. If you had like actually external memory to make use of, you could read the input once from left to right and then store that input and then do whatever you want with it. So scanning input once is not maybe perhaps the key limitation. The key limitation, I would say, is that it has a constant number of states, and really the states are the way that a DFA remembers stuff, kind of used as a memory, and there's no other way to remember anything else. So when I say a constant number of states, I mean that it's a fixed number that cannot depend on the input length. That's what constant means, constant with respect to input length, which means that if you have some DFA, let's say it has 251 states, well, it's fixed once and for all, and this DFA with 251 states has to be able to handle all input strings, any length input string, right? So that the input length might be 1,000 bits, 1,000,000 bits, 1,000,000,000,000 bits, no matter what it is, it has to give the correct answer. So that seems very limiting, all right? So a constant number of states kind of means it has constant amount of memory. Okay, good. So now then we want to target basically that weakness, that limitation of a DFA, that it has a constant number of states and no other way to really remember stuff. Now, if we want to then target that and pick a non-regular language, candidate non-regular language, maybe we can think about you know, if you did not have any restrictions, like let's say like if I'm giving you a string and you're gonna, scan it once, you're gonna see the input bits one by one, and then you're gonna do something and make a decision about accepting or rejecting. What is something that you could do that a DFA could not do, right? If I'm giving you an input string, zeros and ones, what operation, what kind of thing that you could do a DFA could not do? Update a variable. Check that the first half of the string is yes. Okay, I'm gonna focus on one thing here. You guys have great ideas. Count, right? A DFA cannot count to arbitrary numbers. You can count, like if I give you a billion length input, you can count like 1, 2, 3, 4 and do that. A DFA, let's say it has like 10 states, maybe it can count up to a 10, but like it can't really count more than that, right? So I think like accounting is like a very simple operation, a very simple thing that we can do that a DFA should not be able to do. So then based on that, here's my candidate, like let's say language. Like consider the language consisting of all binary strings with an equal number of zeros and ones. So I think this would not be a regular language, and we can go ahead and try to prove this, right? Actually, I'll even simplify a little bit this language for convenience. It's easier to write this language. Let's consider the set of all those strings of the form 0 to the n, 1 to the n. So you have some number of zeros followed by the same number of ones, right? So just to be clear, so the empty string is in the language, 0, 1 is in the language, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. So this is an infinite language, and it has this form. And yeah, so now we want to argue that no DFA can recognize this language. So what would be, again, the intuition here? The intuition that we're developing is that it seems like when you are, solving this language, what you would do is you would see the zeros and you would count the number of zeros you see, and then you would count the number of ones you see, and then you would compare those two numbers. So it seems like a DFA would need to remember the number of zeros it sees as it's scanning the input, but it has a constant number of states and really no other way to remember things. So it should not be able to do that, right? So if you told me, for example, hey, I have a DFA with 1,000 states that, solves this language, I would say, okay, you're claiming a DFA with 1,000 states solves this. Let me give you an input with 1,000,000 zeros and followed by 1,000,000 ones. I think that input should really mess up your DFA. Your DFA should not be able to handle that. Okay, you say, well, okay, I came up with another DFA. It has 1,000,000 states now. So fine, it has 1,000,000 states. Now I'm going to give it an input with 1,000,000,000 zeros followed by 1,000,000,000 ones. How is it going to handle that, right? That's kind of the intuition. Now, okay, very good. So this is the intuition. Now, can I call this intuition a proof and be done with it? Is this a proof? Is this intuition a proof that 0 to the n, 1 to the n, this language is non-regular? Absolutely not, right? Now, your intuition in this case is true, but you have to be careful, right? Here's another language, related language, where you can apply, it seems, the same kind of intuition. You can say, so this is the language of all those binary strings, such that the number of 0 ones and 1 zeros occur equally often. Okay? And in this case also, it seems like, well, to decide to solve this language, it seems like I would need to count the number of 0 ones and the number of 1 zeros, compare those two numbers and see. So it seems like this also requires you to count. But careful, this is actually a regular language, right? So your intuition actually is not correct, would not be correct in this particular case. Why? Well, it turns out in this for this particular language, actually, there's a hidden structure that doesn't require you to count, right? You can do this without counting. So that is to say, intuition is of course very good, and you're going to build your argument based on your intuitions, but intuition is not a replacement for airtight proof. So that's what we want. Good. So now I'm going to give you the argument. A key component of the proof is going to be the pigeonhole principle. So let me quickly remind you, the pigeonhole principle is if you have k plus 1 pigeons, but only k holes, and you're going to put the pigeons into the holes, then you know that at least 2 of the pigeons have to get cozy and share a hole, right? So that's the pigeonhole principle. I'm sure you've seen it before. Very simple principle, and it's going to come in here. Okay, so let me now give you the proof idea, right? So this is the language we want to show that it's not regular. And what do you think is going to be the overall proof strategy? Is it going to be a proof by induction? Is it going to be a proof by... Yeah, okay, you got it, right? Contradiction, right? Because in some sense, when we were building the intuition, that's kind of how we reasoned about it, right? I said, well, if you say that you have a DFA for this language with some number of states, then I'm going to like feed it an input that is much longer than the number of states you have. And that should like mess things up for you, right? And that's exactly what we will want to do. So let's assume that, for the sake of argument, that there's a DFA with 6 states that decides this language. Now, why am I saying 6? Because I have room to fit 6 states on my slide here. That's the only reason. The argument is going to be the same, no matter what 6 is, like arbitrary k, it's going to work. But I'm just saying 6 for now as an example. Okay, so let's draw that DFA, right? I have 6 states. There's some transition. Imagine some arbitrary transitions here. I cannot draw you the transitions because there's no DFA for this language, but we imagining some DFA exists. And then what? Then, as we said, like, let's feed this now DFA a long input, right? Like more than 6 characters, right? So let's give it like all zeros. All zeros is fine because as the machine is reading the zeros, it doesn't know like, oh, will there be an equal number of ones followed later on? So that way we can sort of confuse it. And let's imagine like we run it on this input, right? So the empty string starts at Q0, and then you read a 0 that takes you, let's say, to Q2. You read another 0, maybe that takes you to Q3. You need another 0 that maybe takes you to Q1. Another one, maybe now you're in Q5. Another one, now you're in Q4. And then another one, and now we are back to Q3, right? So after reading 2 zeros and 6 zeros, something interesting happened. Now, the first time, 2 strings ended up in the same state in Q3. Okay, now, this should be a problem, right? Because if you think about it, from the DFA's perspective, it's kind of oblivious to the difference between 2 zeros and 6 zeros. Both of them end up here, and that should kind of be a problem. Who can see? Why is this a problem? Would it be a problem to have 2 zeros and 6 zeros end up in the same state? Exactly, right? So you're like, consider like having 2 ones or maybe like 6 ones afterwards, or let's say just 2 ones, right? What should happen? So let me explain this. I think you guys kind of see the argument now, right? But let me explain what's going on. Now, we have 2 zeros and 6 zeros ending up in the same state. Okay, state Q3. Now, what this means is that once these 2 strings are joined, in some sense, they're joined then forever, right? So if I append any string, so if I were to append, let's say, a 1 to 0, 0, and 6 zeros, so 0, 0, 1 and 6 zeros 1, well, again, they will be in the same state, right? Or if I were to append to these 2 strings 1, 0, 1, well, they will end up in the same state, right? So 0, 0, 1, 0, 1, and 6 zeros 1, 0, 1 is going to end up in the same state. Let's say Q2, for example. So the observation is basically that, and I will disappear now, for any string z, if you append z to 2 zeros and 6 zeros, they end up in the same state, right? So once they're joined, like they're joined, these 2 strings. And now this is a problem, right? Because why? As you guys suggested, if you consider the string z to be 1, 1, right? Well, these have to end up in different states because 0, 0, 1, 1 should be accepted and 6 zeros 1, 1 should be rejected. And now this is where we are using the assumption that our DFA recognizes that our DFA solves this language 0 to the n, 1 to the n. And that, of course, has to come into our argument, right? I mean, we have to use the fact that this DFA, we're assuming, is solving the language 0 to the n, 1 to the n. And this is where we use it. We say, well, if it's solving correctly this language, then we know that 0, 0, 1, 1 should be an accepting, should end up in an accepting state, and 6 zeros 1 1 should end up in a rejecting state. But a state cannot be accepting and rejecting at the same time, right? And that is the contradiction. Okay? So this is basically the proof idea here. Okay? So let me highlight the pigeonhole principle once again here. So what happened is that we thought of these strings, like the empty string 0, 0, 0, and so on, as pigeons. And we know that every string ends up in some state in the DFA. And the state is like the hole that the pigeon goes to. So the empty string goes to Q0, right? It starts at Q0. Maybe like 0, that pigeon goes to Q2. And, you know, you basically, these strings start going to holes, different holes perhaps. But then, you know, if you have, I have 6 states, if I have 7 pigeons, if I have 7 strings, then I know 2 of these strings must end up in the same state. 2 of the pigeons have to go to the same hole. And that was key in our argument, right? And it didn't really matter if it was like 2 zeros and 6 zeros that ended up in the same state. If it was like 3 zeros and 4 zeros, that would still be fine. We could still carry out the contradiction. Okay, so not enough holes for all the pigeons. Yeah, so now I'm gonna actually tell you how to write this up, right? So this, we kind of built our intuition. We're pretty much close. Like, I mean, if you just now write this up a bit more properly, you get a full proof write-up. And let me show you quickly how that goes, right? So this is a proof by contradiction. So we're gonna say, assume for the sake of contradiction that there exists some DFA that solves the language L that we're interested in, here, 0 to the n, 1 to the n, and let k be the number of states of this DFA. Now, what are we going to do? We're going to consider our pigeon set, okay? So consider the following set of k plus 1 strings that we think of our set of pigeons. So what's the k plus 1 strings that we sort of considered implicitly in the argument? Well, we looked at the empty string 0, 0, 0, 0, 0, 0, all the way up to and including 0 to the k. So that's a set of k plus 1 strings. And now by applying the pigeonhole principle, we know that 2 of these strings, let's call them x and y in P, must end up in the same state, right? So this is where we apply the pigeonhole principle to say that 2 of x and 2 strings in P, let's call them x and y, end up in the same state. Then what did we observe? We said, well, first of all, okay, let me expand on this a little bit, and I'll disappear actually here because I don't have room for myself. So what this means, when you look at the structure of the strings in the set P, what this implies is that there exists I and j, you know, I different from j, such that 0 to the I and 0 to the j end up in the same state, right? We think of x as 0 to the I and y as 0 to the j. Then now, the other observation is that now, once you end up in the same state, now it doesn't matter what appending string I use. So for all strings z, I know 0 to the I z and 0 to the j z must end up in the same state, right? And then we are almost there, right? So now you say, okay, well, now consider though the string z to be 1 to the I. Well, when you take z to be 1 to the I, then 0 to the I z is going to be equal to 0 to the I 1 to the I, and this must end in an accepting state. On the other hand, 0 to the j z, which is going to be 0 to the j 1 to the I, must end up in a rejecting state because I is different from j. And this is the desired contradiction, right? Because on the one hand, we say, look, 0 to the I z and 0 to the j z, no matter what z is, must end up in the same state. On the other hand, when you consider a particular z, which is 1 to the I, we see that they must actually end up in different states. One accepting, one rejecting. And that's the contradiction. And then we can put a box here, and this is the full argument. So I see one question, why this proof can't be applied to 1010110? I love that question, right? So that's exactly the kind of question you should be asking. This is like what it means to dig deeper and understand something better. I'm not going to tell you. This is exactly what you should be figuring out. So go through the proof and see if you can make it work with 10101. It should break, right? And see where it breaks and why it breaks. And then once you see that, you can go and actually start thinking about, oh, can I actually draw a DFA for this? Actually, and you should be able to. Okay, but I mean, that's a great question. This is exactly the kind of question you should be asking. Okay, so now you have a proof like this, and you guys already started asking good questions, but you want to dig deeper, right? So you don't, when you read a proof in the notes, you don't want to just read it once and be like, you verify that the proof is correct and move on, right? You want to dig deeper and understand what's going on better. So you want to ask, like, what are the high-level steps here that we used? Why did this argument work? Can I extract the key ideas that made it work so that then I can use it in the future? Okay, so this is the kind of thing you should be doing yourself when you read a proof, and I'm going to do it for you now. So after reading this proof, I would be like, okay, so there are maybe 3 high-level steps here. You set up a proof by contradiction. We pick our pigeons, and then we reach a contradiction from there. So what do these mean? So setting up a proof by contradiction, assume that the language is regular, okay? And so DFA with k states, let's say, recognizes it, solves it. Then you pick your pigeons. So you identify k plus 1 strings. So you had k states. We identify k plus 1 strings as our pigeons. Okay, and by pigeonhole principle, we know that 2 strings, 2 pigeons, x and y, must end up in the same state. Okay, now that means that for any string z, xz and yz must end up in the same state, right? So once 2 pigeons fall into the same hole, they fall in love, and then they're joined together forever. You can't separate them anymore. They are not distinguishable. They're not separable, right, from the DFA's perspective, right? And then you reach a contradiction from there. You identify a particular z that does separate these 2 pigeons, okay, such that, xz, one of xz and yz is an L, but not the other, okay? So now you sort of now understand the proof a little bit better here, but, you have to dig deeper still, because you have to see that, look, the way step 2 and step 3 works, they have to work together, right? So in particular, you cannot just pick any set of pigeons. So one question you should be asking yourself is, can I just pick any set of k plus 1 strings and make the argument work? Not necessarily. You need to pick your pigeons carefully such that you can carry out the contradiction step here, that you can do step 3. In particular, consider, for instance, this one, right? Would P like 1, 1, 1, 1, 1, 1. So we chose, in the previous example, we chose the string 0, 0, 0, 0, 0, 0, and so on. And that worked. Would the strings, you can ask, why did we choose those strings? Would it work if it was like all ones? Well, hopefully you see that it wouldn't work, right? Because every string in P starts with a 1, which means that no matter what appending string Z I use, it's going to be rejected by, should be rejected by the DFA. So I cannot carry out the last step to say that, oh, one of them is going to be accepting and the other rejecting. I cannot get an accepting string from this pigeon set. So this wouldn't work, right? So now you start to understand, oh, I have to pick my pigeons carefully. And also, when you're applying the pigeonhole principle, you don't have control over which 2 pigeons end up in the same hole. So it has to work no matter what 2 pigeons end up in the same hole. Okay, so now you make these kinds of observations. Now you're understanding things better. So I hope you see that there's a difference between reading a proof and verifying that it's correct. Like you can go through the logical steps and say, oh yeah, that works, and then move on. But you can ask deeper questions like this to really understand what's going on and get a better intuition, better understanding. And that's exactly what we would like you to do. Okay.